Hello, I'd like to take a little bit of time to talk about and show you some conceptual information, a little simulation demonstration relating to momentum and collisions, so conservation of momentum primarily. So I'm going to the PhET Collision Lab. Click on that, and we're going to explore one-dimensional motion. So you can see here we've got two balls. We can change things around. We can change the mass. We can change the position by adding numbers here, but we can also just drag it and move it. The position is not going to be something that is really important. The mass is, and the velocity is. So I'm going to start with two balls. Each of them have a mass of 1, and so they have the same mass, they have the same velocity, the same speed, but in different directions. So the momentum you can see of each one. So 1 kilogram meter per second, because remember momentum is m times v. So 1 kilogram times 1 meter per second, of course, is 1 kilogram meter per second. We've added this here, so kinetic energy. The kinetic energy of the system once it's moving. So when it's stopped, of course, they have no kinetic energy, but when they're moving at that velocity of 1 meter per second, so kinetic energy is 1/2 mv squared. So mass 1 kilogram, v squared, 1 times 1 is 1, but 1/2 times 1 times 1 is 1/2 of a joule. So each of these balls has 1/2 a joule, so the total together is 1 joule. So notice the momentum arrow. So the momentum arrow for 1 is pointing to the right, the momentum arrow of 2 is pointing to the left, and then just here's a little diagram down here that shows those two arrows. So what I'd like you to think about is I'm going to hit start again, and in a fraction of a second they're going to hit each other. Think about what the momentum will be afterwards, the momentum of each object after they collide. So you can look at these values down here. You can think of the arrows, so what will the arrows look like, and they're represented here, and what will the kinetic energy be. So you can stop and think if you want, or you can think really quickly. So we have moved into a collision. Now 1 is moving, it used to be moving to the right, now it's moving to the left. 2 was moving to the left, now it's moving to the right. So the momentum of each object is the same magnitude as before, but now ball 1 has a negative momentum, ball 2 has a positive momentum. Notice that the overall momentum of the system stayed the same. Before it was 1 plus -1, which equals 0. And then it was -1 plus 1, which equals 0. Also notice that the kinetic energy stayed the same. So that is with two balls, same mass. So now we're going to go back to same speed. Just checking at my notes here. Now we're going to go to, we're going to double the mass of ball number 2. So notice what happens. The momentum arrow is twice as large. So the initial momentum of the blue, again, once it gets going, will be 1 kilogram meter per second. 1 kilogram times 1 meter per second. For the pinkish ball, is that pink, purple? I don't know, I'll call it pink. That's a mass of 2 kilograms, so momentum is 2 times -1 or -2. So the momentum before a collision is now 1 plus -2 or -1. And notice this momenta diagram Now we've got the total momentum is to the right a value of 1 box. It looks like one of these boxes represents 1 kilogram meter per second. And notice the kinetic energy is a little bit greater. So this one still has the same kinetic energy as before. Now we've got 1/2 times 2 kilograms times 1 meter squared per second squared. So the kinetic energy initially of this one is 1. So 1 plus 0.5 is 1.5. So predict what's going to happen to the motion of these when they collide. And I didn't point this out before. Notice they have elasticity as 100%. So totally elastic, which means they bounce off each other just like 2 billiard balls would, or 2 metal BBs would. Even those aren't perfectly elastic collisions, but these are perfectly elastic collisions. So again, predict what the momentum will be, the total momentum will be afterwards, the kinetic energy will be afterwards, and also you can predict what the momentum of each of the objects will be. All right, so afterwards, first off, we've got the momentum over here. So the velocity of ball number 1, the lighter ball, now has a greater speed than before. Its speed increased by 67%, and it's going to the left just like it did before. The pink ball is moving to the right like it did before at a slower speed. But the sum of those two, if you calculate the mass times velocity for each one, we still get the same total momentum. So the momentum before the collision and the momentum after the collision stays the same. Notice also in this case the kinetic energy stayed the same as well. So for elastic collisions, it looks like the momentum stays the same and the kinetic energy stays the same. Let's do this one more time. And we're just using the same basic numbers as before, but now we're going to triple the mass of that first ball. And so again, predict what's going to happen. This time the kinetic energy is greater because we're increasing the mass of the ball, and you can calculate the 1/2 mv squared of each item if you want to. But notice that once they get moving, in each case, ball number 1 has had the same momentum, so that arrow has been the same length each trial. The momentum arrow, and it's always pointed to the left initially. The momentum arrow of the pink ball, I'm sorry, to the right. The momentum arrow of the pink ball is always initially pointed to the left, but it has doubled and now tripled in length. So predict what you think will happen to the blue ball and the pink ball after they collide. Just describe in your head or jot down in your notes what the motion will be, and then also describe in your head or jot down in your notes what you think the final momentum would be. Well, first off, guess what the total momentum would be after the collision, and then what the final momentum would be for both balls after the collision, and then think of the kinetic energy. All right, interesting. So in this case, I'm going to just move this out so you can see the arrow length. In this case, ball number 2 stopped, so its velocity is 0. Ball number 1 now is moving off to the left, or it would have been had I kept the play going, moving off to the left at 2 meters per second. So the total momentum afterwards is still the same, a total of -2 kilogram meters per second. So the total momentum is dominated initially by the momentum of the pink ball, which is going at the same speed as the blue ball, but since it's 3 times more massive, it dominates the momentum. So you might be thinking, well, I didn't really predict that ball number 2 would stop, because you could say, well, why isn't it that ball number 1 bounces backward, like the second trial? Ball number 1 bounced back faster, but ball number 2 still moved a little bit. So why didn't ball number 1 in this case bounce back faster than trial 2, but ball number 2 still bounce back a little bit? So maybe going at a tenth of a meter per second or something like that. The reason is because for elastic collisions, kinetic energy has to be conserved as well. So for the momentum to be conserved, the m times the v before and after, there are a lot of different ways that you could have mass 1, final velocity 1, plus mass 2, final velocity 2, summing to -2. But only one of those combinations of numbers would also give you a kinetic energy that is conserved, and that is the one that you see right here when ball 2 comes to a stop. So in elastic collisions like this that are elastic, both momentum and kinetic energy are conserved, and that helps us figure out the numbers here. So we're going to go back again to this case. But now, instead of an elastic collision, we're going to go with an inelastic collision. Totally inelastic, which means they're going to stick together. So predict what's going to happen to the momentum after. So notice this diagram looks just like the very first time when it was here. I moved this slider, doesn't change anything with the numbers or any arrow lengths or anything like that. And it didn't change the kinetic energy. Predict what's going to happen to those two balls when they collide and after they collide. Think of what's going to happen to the momentum. Think of what's going to happen to the kinetic energy. And let's see. No, I was checking my notes here, see if there's anything I want to say. All right, so they collided with each other and they completely stuck together. So the momentum afterwards is 0. So the momentum was conserved because the momentum before was 1 and -1. The momentum after is 0 plus 0. 1 plus -1 and 0 plus 0 all equal 0. In this case, the kinetic energy is also 0. So kinetic energy was lost. Momentum was conserved, but kinetic energy was not. Let's think about that. Think about where that energy may have gone. And we'll do one more trial. You can probably guess what we're going to do here. 2 and 1, -1. So the initial momentum is 1 kilogram meter per second to the left. So -1 kilogram meter per second. Kinetic energy 1.5, just like it was initially when it was in an elastic collision. So think about what's going to happen to the momentum after. Think of what it's going to sort of generally look like broadly, and then what the numbers will look like. So momentum was still conserved. Initially, it was 1 plus -2, so -1 kilogram meter per second. Afterwards, it's -1/3 plus -2/3 is still -1 kilogram meter per second. So momentum is still conserved, but again, kinetic energy went way down. Before it went from 1 joule to 0 joules. Here it went from 1.5 joules to 0.17 joules. So it didn't lose all the energy, but it's still much less, all the kinetic energy, but it's still much less. So we're going to go one more time. I think before I said there'd be one more, but I want to do something more. All right, so notice here the initial momentum is -2 kilogram meters per second, so 2 kilogram meters per second to the left, and kinetic energy is 2. So predict what is going to happen. So this time we went from -2 kilogram meters per second, so 2 kilogram meters per second to the left, and after we have -2 kilogram meters per second. So once again, momentum is conserved. Notice afterwards they stick together, so their velocity is the same. And in this case, the kinetic energy is even a bigger drop from 2 to 0.5. So think about what might have happened to that kinetic energy. Think of what happens if two things collide with each other. And no collision is perfectly elastic. There's a little bit of a clue. All collisions have a little bit of inelasticity to them. So think of what do you observe when there's a collision? So when there's a car crash, if you're not looking and a car hits a wall, what do you notice if you're not looking? Well, you notice the sound. And then you do look, the collision's over, but you see that the car is all crumpled up. Pieces have flown off. So there is energy taken up to make sound. Sound doesn't come from no energy. So there's energy to deform the materials. The material that doesn't really look deformed has probably undergone a little bit of arrangement at the molecular bonding level. There's probably a little bit of heat generated. So in an inelastic collision, kinetic energy is converted to other forms of energy, sound, heat, deformation of material. And it kind of makes sense that when we had two things of the same mass colliding, that wasn't as violent a collision. Now we have something 3 times the mass colliding with the smaller object. That would be, sort of qualitatively speaking, a more violent collision. So it makes sense that more kinetic energy, that more damage is being done, more noise is probably generated. So more of that kinetic energy is going into creating noise, bending the material, creating heat, and so on. So there's a greater kinetic energy loss. I hope this helps. When you get into the chapter, you'll be reading a lot about numbers and algebra and that sort of thing, but this gives you a good feel for it. I'd also encourage you to go to the Fat Collisions lab and toy around with things yourself. Thanks.